Recording. Cool. Okay, so today we'll continue to work through lecture set number 6. In lecture set number 6, we're talking about some sort of like extra topics at this point. So to this point, we have seen all of the different sampling strategies that we're interested in studying. So we talked about simple random sampling. We talked about systematic sampling. We talked about stratified random sampling. And then we talked about cluster sampling and two-stage cluster sampling. So those are the 5 strategies that we wanted to discuss for estimating a population mean or a population total or a population proportion. Within those units, we did deviate in some cases. So we discussed, for example, properties of estimators. We talked about relationships between, say, systematic sampling and simple random sampling. We saw how, as you extend the clustering scheme, everything sort of relates back to the simple random sampling scheme. So most of the estimates have a very similar form. For example, in stratification, you're really just weighting the simple random sample estimates. We also talked about ratio, regression, and difference estimation. And each of those approaches we saw in the context of at least one of those schemes. So for example, we used ratio estimation within simple random sampling. We used ratio estimation within stratification. We saw how the cluster sampling estimates are actually ratio estimates in their, well, they're very similar to ratio estimates in the forms they take on. So there was quite a bit of overlap between the different topics, and we used different estimation strategies within certain sampling schemes. But in general, again, what we've talked about are 5 main schemes and ways of estimating some population quantity within each of those different schemes. In lecture set 6, what we're talking about, or what we're starting off with, is just a discussion on how the estimators will change if we don't assign equal weight to each of the observations in the sampling frame. So with simple random sampling, for example, we assume that every observation has the same probability of being selected. So every unit in the frame has the exact same probability of entering into the sample. We also assume with simple random sampling that when we sample, we won't have, or we sample without replacement. So every observation has the same chance of being pulled, but each observation can only appear once in the sample. So in this lecture set, effectively what we're doing is we're looking at how our estimators and our samples can change if we, for example, don't allow for, or if we allow for observations to be repeated within the sample, and what will happen if we do not assign equal probabilities to each of the observations. It's a relatively short lecture set. I'm not overly confident that we're going to need the entire period today to finish it, but we'll see. Maybe questions will come up and whatnot. But with that being said, we'll just work through it and we'll get to where we get to. If we complete it, great. If not, we'll finish it on Tuesday or on Wednesday next week. Okay, so this is the last day of March. Can you believe it? Okay, so in this illustration, we are looking at an example of sampling with replacement from a population or a sampling frame. It should be sampling frame because that's what we define U to be, with 4 elements in it, 1, 2, 3, 4, and with equal probabilities of being selected. So the delta 1 through delta 4 are all equivalent. There's 4 elements, so that means that they're equal to a quarter, or 1/4. Okay, in part A, we are asked, what are the probabilities of observing each possible sample of size 2 when sampling with replacement? Okay, so in the first column of this table, we have listed out all of the possible samples that we could observe. In the second column of the table, we are giving the probability of selection for each of the different samples. Okay, so that's this column here. All right, so we are sampling with replacement, which means that the probability that each unit enters the sample is never going to change. Now, for the first sample, we have the sample that contains the elements 1, 2. We have P of S is equal to 2 times 1 over 4 times 1 over 4. The 2 represents the fact that the sample can be either 1, 2 or 2, 1. So there's two ways of observing the sample with these units included within them. So the leading 2 is just representing, again, the fact that we can see observation 1 and then observation 2, or we could see observation 2 and then observation 1. Following that, the probability of selection for each unit is equivalent, so they're all equal to a quarter in this case. So for example, for the sample 1, 2, we have 2 times 1 over 4 times 1 over 4, which gives us 1 over 8. And this is going to be the same calculation for all of the samples that have that have two unique values included within them. The last 4 samples are the samples that show that we are sampling with replacement, right? So in this case, we have 1, 1, 2, 2, 3, 3, and 4, 4. So these last 4 samples all have probabilities 1 over 4 times 1 over 4 because there's only one way of observing the sample with 1, 1 in it, or with 2, 2 within it, etc. Okay, so in part B, we want to compute mu hat for each sample. So that's going to be this column here. All right, this is a pretty straightforward calculation. We're basically just taking the elements and averaging them. So here we're going to have 1 plus 2 over 2, which is equal to 1.5, right? Here we're going to have 1 plus 3 over 2, which is equal to 2. 1 plus 4 over 2, which is equal to 2.5. 2 plus 3 over 2, which is also equal to 2.5. 2 plus 4 over 2, which is equal to 3. 3 plus 4 over 2, which is 3.5. And then each of these will just be equal to the values within them. Okay, any questions? I assume that was probably pretty straightforward, right? Okay, in part C, we want to show that our estimator is unbiased. Okay, so first of all, to do this in this situation, we're going to do it empirically. So we're actually going to use the values that are available to us to show that it's unbiased. Now we know that mu tilde is unbiased when its expected value is equal to mu. So we need, right? We need both mu and mu tilde. So for us, mu is going to be equal to the sum across I and u of each ui multiplied by the probability of observing that element. So this is going to be 1 times 0.25 plus 2 times 0.25 plus 3 times 0.25 plus 4 times 0.25 And that gives us 2.5. All right, actually, sorry, we need to find mu tilde is just the equation. We need to find the expected value of mu tilde. Right. Okay, the expected value of mu tilde is equal to the sum from I equals 1 to 10 in this case. So 10 here represents the number of samples. Right. And this is going to be of each mu hat I multiplied by the probability of observing that sample. Okay, so in this case, we're basically just taking what we have in the previous table and we are writing it out in full. So we're going to have 1.5 multiplied by 1 over 8 plus 2 multiplied by 1 over 8 plus 2.5 multiplied by 1 over 8 plus 3 multiplied by 1 over 8 plus 3.5, 1 over 8, 1, 2, 3, 4, 5 plus 1.52, 2.5. Oh, there's a double 2.5. Plus 2.5, 1 over 8. There you go. Plus 1 times 1 over 16 plus 2 times 1 over 16 plus 3 times 1 over 16 plus 4 times 1 over 16, which is equal to 2.5. Therefore, mu tilde is unbiased. Okay. Any questions? Okay, so that's our example for effectively showing that an estimator for the mean that's collected through sampling with replacement is unbiased. So now what we're going to do is we're going to work through the same illustration, but in the case where we sample without replacement. And then what we're going to do is look at how we would adapt this to finding the total, which isn't exactly as straightforward as it was in the SRS cases or in any of the other design cases that we have seen, because in those cases, we effectively just took our estimate for the mean and multiplied by the population size. In these situations, it's not quite the same approach, but we'll see that momentarily. Now, in a second illustration, we take the same population and we sample without replacement now. So the changes here are going to be fairly subtle. So we can start by constructing a table like the one that we had in the previous illustration. Okay, so in this case, if we sample without replacement, it's only possible to observe 6 samples where each sample has a unique number of elements. Okay. All right, now the probabilities that are associated with each sample. So we'll start with the same leading 2. So in this situation, you can still observe 1, 2 or 2, 1. So we're going to accommodate for the order. Then we would have 1 over 4 multiplied by 1 over 3. And that gives us 1 over 6. And this is going to be a consistent calculation for all 6 of these samples. Okay, so here's our probability of S. Okay, and then we will find our estimates for the mean. This is going to be done the same way that it was before as well. So in each case, we're just taking the values that we have and averaging them. Oh no, this would be, yeah, 2.5, 2.5, 3. Okay. So in the first column, we have A. In the second column, we have A. In the third column, we have B. All right. Now we want to show that mu tilde is unbiased for mu. This is also going to be done in the same way that it was before. So here, we're going to have the same estimate for mu. So the true mean is equal to the sum for I and U of the ui multiplied by the delta I. So that's going to give us 2.5. There's no difference there. And then we're going to have the expected value of mu tilde is going to be the sum from I equals 1 to 6. In this case, 6 again represents the number of samples that we have observed of each mu I hat multiplied by the corresponding probability of observing that estimate. This is going to give us 1 over 6 multiplied by 1.5 all the way up to 3.5, which is equal to 2.5. Therefore, mu tilde is unbiased for oh. Any questions? Okay. All right. So if we want to compute the total based off of a sampling with replacement or sampling without replacement strategy, we of course would have two different estimates. In the case that we sample with replacement, an unbiased estimator of the population total is given here, and I'll just call this equation 1. So you can see that we have tau tilde is equal to 1 over n times the sum from I equals 1 to n of yi over delta I. Okay. So this would basically be similar to the thing that we had before. This is going to be a number of samples in this case. Same thing here. All right, when we sample without replacement, the UI changes on each draw. Okay, which means that, well, basically what I'm saying is when we sample without replacement, we know that the probability associated with each unit is going to change, right? So we just saw an example of where we took the first element and it had a probability of being selected of 1 over 4. And then the second element's probability of being selected is now 1/3 because there's only 3 elements left within the frame to select from. So it's going to be the same issue with estimating the total. So each time we draw a unit out, we change the probability of observing the next unit. So we can replace the delta I with the average probability that the ui is selected, which we call pi I over n. Okay, so pi I is going to be this probability that ui is selected. If we do that, our estimator for tau tilde becomes the sum from I equals 1 to n of the yi over the pi I. So let's just take a look at how this is going to work, because it's easier to illustrate than it is to explain. All right, so in this situation, we are going to sample without replacement. We have the same population, so we have a population with units 1, 2, 3, 4. The probability of observing each of the 4 units is 0 0.1, 0 0.1, 0 0.4, 0 0.1. We want to show that tau tilde is unbiased for tau for all samples of size 2 when sampling without replacement, and then compute the variance of tau tilde. Okay, so part A is effectively going to mimic what we had just done in our illustrations of showing that mu tilde is unbiased. The difference here, of course, is that we're working with tau tilde, and we're basically doing parts A, B, and C all in one large step. Okay, so we'll start off by writing out the samples. So those are going to be the same 6 samples that we had worked with in the previous illustration. All right, now let's compute the probability of observing each sample. So first, we'll have our leading 2, right? So we know that we can observe each of these samples in either order. So we can go 1, 2, or we can do 2, 1. All right. Okay, so the probability of observing the first unit is going to be 0.1, right? So the probability that we pull the 1 is 0.1. The probability that we pull the 2 is 0.1. The probability of observing the second unit is going to be 0.1 divided by what's left over, which is 0.9. So we've taken the first unit out, which contributed a probability of 0.1. So that means the remaining probabilities to be selected from is equal to 0.9. So now we have 0.1 over 0.9. Okay. Right, any questions about that? Okay, well, let's take a look at the second one. So in the second case, we have to consider each scenario separately. So this scenario where 1 enters first and then 3, and the scenario where 3 enters first and then 1. So if 1 enters first, we have 0.1 plus, and then we'll have 0.4 divided by 0.9. Oh, wait, sorry. I don't know why I'm adding these. There we go. Okay, and then we add the second example. So the second scenario is where the 3 enters first, and then the 1 enters. Okay. Any questions? Okay, so for 1-4, it'll be the exact same calculation that we saw for 1-3 because the probabilities that are associated with each of those units are the same. And that's also going to be true for 2-3 and for 2-4. So we can mimic this calculation for each of these samples. In the last sample, we have two values that both have the same probability of being selected. So now we'll have the leading two to represent the fact that we can observe 3-4 or 4-3. And then we'll have 0.4 times 0.4 over 0.6, which gives us 0.533. Okay. Any questions about the probabilities? All right, so now let's talk about estimating tau hat for each of the different samples. So when sampling without replacement, tau hat I is equal to the sum from I equals 1 to n of yi over pi I. And actually, I just realized that I made a mistake here. This would not be number of samples. Tau tilde, tau tilde. This would just be for each individual sample. But that'll become more clear here. Okay. Okay, so we have to find each pi I for I in U. There we go. All right. So basically the way that this works is, for example, pi 1 is going to be the complete probability of observing unit 1. So that means that we would have 0.0222 plus 0.111 plus 0.111, which is equal to 0.2444. Pi 2 is going to be the probability of observing unit 2. Okay, so that's also going to be 0.0222 plus 0.111 plus 0.111, which is equal to 0.2444. I guess it would technically be 0.2442, right? No, 444. No, 442. All right. Pi 3 is going to be the sum of the samples that include probably the third unit. So you'd have a 111, another 111, and then you'd have the 0.5333. So you'd have 0.111 plus 0.111 plus 0.5333, which is 0.7553. All right, and then pi 4, from a similar logic, will have the same All right, now we can use this information to find each of the tau hats for each sample. So I'll show you an example calculation here. Okay, so for example, tau hat 1 is going to be 1 yeah. Okay, so tau hat 1, where I can't use I here. Sorry, I'm going to call this mixing up all the values. Okay, let's just call these J's, just so it doesn't get confused with the values inside the sample. And then we can sum across J later. There we go. Okay, so J is going to run from 1 to 6 because we have 6 samples. J in 1 to 6. Can't use curly brackets. 1 to 6. It's a this is a comma. This is a J. There we go. J in 1 to 6. Okay, so tau 1 is going to be 1 because the first value in the first sample is a 1, divided by the probability of observing the 1 plus 2 divided by the probability of observing a 2. And that's equal to 12.27496. Right. And then as another illustration, like for example, let's say we took tau 2. So tau 2 is the second sample. So you're going to have a 1 divided by 0.2442 plus 3 divided by 0.7553. And that's going to be 8.0642. And just one more, just to get the flow. So tau 3, this would be the sample with 1 and 4 in it. So okay. Any questions about that? Okay, so following that process, we have 12.27496, 8.0624, 9.3860, 12.1540, 13.4776, and 9.2652. And we saw examples of the first three. So, just for clarity, these three values here. Those are these three values here. Okay, so each of those 6 totals are going to be computed using the same idea that we have below. Value in the sample divided by the corresponding pi for that value. Now, our actual goal here was to show that this thing is unbiased. So going back to the original goal, we want to show that the expected value of tau tilde is equal to tau. Okay, so tau is going to be the sum from or across I and U of each ui. So that's going to be 1 plus 2 plus 3 plus 4, which is 10. Right, so that's just the total of all the population elements. And then the expected value of tau tilde will be the sum from j equals 1 to 6 of the tau j hat multiplied by the probability of observing each sample. So this is going to be 12.27496 multiplied by 0.0222 plus 8.0642 multiplied by 0.111 plus 9.3860 multiplied by 0.111 plus 12.1540 multiplied by 0.111 plus 13.4776 multiplied by 0.111 plus 9.2652 multiplied by 0.5333. Okay, and then this should give us 10. Surprise, surprise. Right, so therefore, tau tilde is unbiased for tau. Okay. So the overall process is exactly the same as what we saw for the means. I mean, in terms of like what we are trying to accomplish and how we actually go about showing that the estimator is unbiased doesn't change from situation to situation. The big difference is really just the form of each of the tau hat i's and how we have to utilize these pi i's within the calculation to find tau. But once we have that part done, everything pretty much mimics what we had before. Any questions? Okay, in part B, we want to find the variance of our estimator. So this will be done simply by finding, okay, so the 0.9, so on the first draw, we take out an element whose probability is 0.1. Okay, so the total probability, like, so the sum of the delta I for I in U, let me write that a little cleaner. Okay, so the sum of the delta I across all values in the frame is equal to 1. Okay, so therefore the 0.9 is 1 minus the 0.1, which is the probability that is removed when you take out the first sample. And that's the same idea with the 0.6 here. So this is 1 minus the 0.4, which is from the first element that's taken out. Yeah, exactly. Yeah. Does that make sense? Yeah, this part's sneaky. I remember working through this when I was first trying to figure this out, and I found it really like kind of sneaky as well. Any other questions? Okay, so to find the variance, we're going to sum from j equals 1 to 6 of each tau hat j minus the true tau multiplied by the probability of observing the sample squared, right? So that's basically just the definition of the variance. The only difference here is that we don't have a consistent probability, so you don't get the 1 over n out front because we can't just pull the probabilities out because they change with each of the samples. Okay, so for example, the first calculation here will be 12.27496 minus 10 squared times the probability of observing the sample, which is 0.0222. All right, and then the second calculation would be the 8.0642 minus 10 squared multiplied by the probability of observing that sample, which is 0.111. And then I'm just running out of room. So this is going to be the same pattern for the remaining estimators from the sample. So we're just going to take each estimator, subtract 10, square it, multiply by the probability of observing that sample. And this should give us something in the area of 2.721. Any questions? Okay. All right, so this idea of sampling with unequal weights can also be translated into our cluster sampling schemes. So we have already studied cluster sampling. We know that what cluster sampling essentially is a simple random sample where you collect groups of observations at the same time, and then you use each of those groups to build an estimate for some population quantity. We have assumed that the probability of selecting each of the clusters is the same in our study of cluster sampling. So if you have, say, 10 clusters available to you and you select 3 of them, each of those clusters has the same probability of entering the sample. But we can take the idea that we have just established and we can essentially give each cluster a different weight of being selected. Now, the funny thing is, when you do this, the result is actually you might agree that the result is actually even simpler than what we had in the situation where we were directly cluster sampling, like we did in lecture set number 5. Okay, so on slide 12, we just have a reminder of what our estimate for the total looks like. This is what we had just studied in the previous illustration. Okay, so in cluster sampling, we can let the delta I within our estimator be equal to little mi over capital M, where again, capital M is the total number of elements in the population, and little mi is the number of elements in each sample. Okay, so if we take this value of delta I and we sub it into our formula for tau hat, we arrive at capital M over little n multiplied by the sum of I in S of the U hat I. Now from this, what we can show is that, this should be a tilde. What we can show is then that the estimator for the population mean, which would be 1 over capital M times the estimator of the total, is simply 1 over little n multiplied by each of the different mu hat estimators from each of the different clusters. So it's a very simple form, which was the point that I was trying to make earlier. So if we basically, if we give unequal weight to each of the clusters in our collection of clusters, we end up with a very simple estimator for the population mean, which is just the average of each of the estimators from each of the different clusters that we have collected. Okay, so on slide 14, we're just summarizing these equations. So we have, for example, mu hat PPS, which is going to be your estimator for the mean under sampling with proportional to size. I think is what PPS stands for. Sampling with probabilities proportional to size. It's a mouthful. Okay. So basically, we're just saying here that if we sample with probabilities proportional to the size, our estimator for the population mean is simply the weight is simply an average of the estimator from each of the clusters that we have collected. And the variance of that estimator is given by 1 over n times n minus 1 over n times n minus 1 multiplied by the squared deviation of each mu hat I around mu hat PPS. And we can show that the total based off of PPS is going to be capital M multiplied by mu hat PPS, which is the same form that we've seen for all of our total estimators throughout the course. And then of course the adjustment to the variance is simply that you have the m squared term out front because the variance operator squares the constant. Okay, now I have an example of this to show how it works. I only have a couple minutes left here. I'm not really gonna have enough time. Okay, so I'll just stop there. I'll show the example. I'll go over this on Wednesday next week and I'll show the example and then we'll move on to some new material. But it's a pretty quick example just illustrating how the estimators work and it's quite straightforward. All right, so with that being said, I'll just stop here. We only have one assignment left, so we're almost done with all of the evaluation parts of the course. That assignment isn't due until next Friday, and it is covering material up to the end of lecture set number 6. So I believe the first question, if memory serves, is a stratification with ratio estimation style question, and then the rest of it is cluster sampling and two-stage cluster sampling. So this material that we're studying now in lecture set 6 and what we'll see next week, this is all kind of additional material that will be on the final but isn't going to be covered on any of the assignments. Next week we have, so Friday we don't have class because of Good Friday, so it's an observed holiday on Friday. Monday we don't have class because it's Easter Monday, it's another observed holiday. So our next lecture actually isn't until next Wednesday. So we have 2 lectures next week on Wednesday and Friday, and we'll use those to go over some new material. And then on Monday, if there's anything left outstanding, we'll cover that as well, but Monday will mainly be dedicated to review before the final exam. Right, so as always, if you guys have any questions, please let me know. And otherwise, I'll talk to you next Wednesday. So have a good long weekend. I hope it's relaxing. And we'll pick up where we left off then.